Hello students, this is Chemistry 101 class. Today we are going to look at study session 6, which is chemical equilibrium and kinetics. The learning outcomes for study session 6 are as follows. 1. Define chemical equilibrium. 2. Explain some chemical processes and rates of reactions. 3. Explain solubility of ionic solids. Now, what do we understand by chemical equilibrium? Chemical equilibrium is said to be the condition which occurs when the concentration of reactants and products participating in a chemical reaction exhibit no net change over time. What is Le Chatelet principle? Actually, this principle is the principle that is guiding this chemical equilibrium and is popularly known as Le Chatelet principle, which states that if the temperature, concentration, volume, or partial pressure of a chemical system at equilibrium changes, then the equilibrium shifts to compensate for the change. Now, what do you mean by dynamic equilibrium? When you look at the screen, you will see that reactants, both the reactant and the products, they have the same composition. They have the same amount. In a situation where you have such scenario, it is being referred to as dynamic equilibrium. Then what is equilibrium expression? Equilibrium expression for a chemical reaction may be expressed in terms of the concentration of the products and that of the reactants. Mathematically, it can be expressed as concentration of the products raised to power x all over concentration of the reactants raised to power y, where x and y are the number of moles of reactant and product respectively. Now, let's consider these reactions. The reaction as it is written on the board, as I've taught you in the previous session, that the reactant is on the left side, while the product is on the right side. Now, when you look at that, you can write equilibrium expression for this equation as concentration of C raised to power L times concentration of D raised to power M all over concentration of A raised to power J times concentration of K B raised to power K, where K is the equilibrium constant. The A in the square bracket is the molar, the square bracket is representing the molar concentration for both products and the reactants. And this K is referred to as equilibrium constant. But before you can use the coefficients which represent the mole ratio in this equation, the equation have to be balanced. What is the equilibrium constant? Equilibrium constant is the ratio of the equilibrium concentrations of the products raised to the power of their stoichiometric coefficients to the equilibrium concentration of the reactant raised to the power of the stoichiometric coefficients. Consider this reversible reaction. A plus B giving us C plus D. You can see that the arrow is pointing to both directions. This specific arrow is peculiar to equilibrium reactions, meaning that as product is forming, is also reversing back to the reactant, and this kind of reaction is known as reversible reactions, as we will see later. What is the significance of this equilibrium constant? Equilibrium constant can be large, it can be small, it can be zero. When K is large, that is equilibrium constant is large, then the equilibrium favors the reaction to the right, and there are more products than reactants. When the equilibrium constant is small, the equilibrium favors the reaction to the left, and there are more reactants than products. But when we have equilibrium constant to be equal to 0, the reaction may be considered not to occur. If the values for the equilibrium constant for the forward and reverse reaction are nearly the same, then the reaction is about as likely to proceed in one direction, and the amount of reactant and products will be nearly equal. And this type of reaction is considered to be a reversible reaction. Therefore, when you have two reagents, two products, it can be written as A plus B going to C plus D. Therefore, a reversible reaction is a chemical reaction where the reactants form products that in turn react together to give reactants back. Reversible reactions will reach an equilibrium point where the concentrations of the reactants and product will no longer change. There are some factors that do affect this equilibrium position, and these factors are as follows. We have effects of change in concentration, effects of change of pressure, effects of change in temperature, and effects of change of catalyst. Now, let's look at how these changes affect the equilibrium position. For the effects of change in concentration, by increase or decrease the concentration of one of the reactant or products, the reaction can be manipulated in the desired direction. To increase the yield of ammonia, the concentration of N2, or preferably H2, should be increased in the synthesis of ammonia. The effect of pressure. Reaction which proceeds in volume, which proceed with decrease in volume, are favored by high pressure. Then when we look at the effects of change in temperature, exothermic reactions will be favored by decrease in temperature, while endothermic reactions will be favored by increase in temperature. What we mean by exothermic reactions is a kind of reactions that heat is released, while endothermic reaction is a kind of reaction that heat is absorbed. Then the last one, effect of catalyst. The presence of a catalyst in a reversible reaction does not affect the state of equilibrium, but only causes the reaction system to attain equilibrium in a shorter period. Now, let's look at homogeneous and heterogeneous reactions. In reversible chemical reactions, the forward and reverse reactions are competing with each other and have different reaction rates. The rates are dependent on time and on the concentration of the reactants and products. Chemical equilibrium occurs when the rate of the chemical reaction is equal in both directions. The concept of equilibrium applies to any chemical reaction in any phase, be it a solid, liquid, gas, or aqueous solution of matter. Solution equilibria can be divided into two subsets: homogeneous solution and heterogeneous solution. Homogeneous solutions are characterized by having only one phase. In contrast, heterogeneous solutions are composed of two phases, and examples are the one written on the screen. For homogeneous mixtures, I have two examples on the screen. The first one is the one that involves the synthesis of methanol, while the other example is the one that involves the synthesis of ammonia. When you look at it, we see that they are all in the same phases. That is, when you look at the equations, we see that all the reactants are in gaseous phase, while the product is also in gaseous phase. In a situation whereby you have both reactants and products in the same phase, it is being referred to as being homogeneous in nature. While the heterogeneous, the fourth example is formation of an aqueous solution of lead 2 iodide, while the second example is the decomposition of sodium hydrogen carbonate. But when you look at these examples, we will see that the phases of both reactants and products are not the same. When you have this kind of scenario, you can refer to it as being heterogeneous in nature. Now, chemical kinetics. Chemical kinetics is the study of chemical process and rate of reactions. What is rate of reactions? The rate of reaction is the rate at which the reactants in a chemical reaction form the products. It is expressed as a concentration per unit time. Now consider the following reaction. A plus B going to C plus D. While small letter A, small letter B, small letter C, and small letter D are the coefficients of both the reactant and product in a balanced equation. Therefore, the rate can be written as K into concentration of A raised to power X dot out multiplied by concentration of B raised to power Y. While in this equation, X will be equal to addition of A plus B, that is small letter A and small letter B, while Y will be the addition of small letter C and small letter D. Now, this will lead us to order of a chemical reaction. What is order of a chemical reaction? Order of a chemical reaction is the sum of the concentration terms on which the rate of reaction actually depends. While the molecularity of a reaction is the number of atoms or ion or molecule that must collide with one another simultaneously so as to result in a chemical reaction. In some cases, order can be the same thing as molecularity, and some other cases it might not be equal to molecularities. Order is just like experimental theoretical value, while molecularity is the actual number of molecules that participate in the reaction. On this basis, chemical reactions can be categorized into three. We have zero order, we have first order, we have second order, then we have mixed order or higher order. For a zero order reaction, it has a constant rate and the rate is independent of the concentration of the reactant. The rate law can be written as rate is equal to K. A first order reaction has a rate proportional to the concentration of one of the reactants. A common example of a first order reaction is the phenomenon of radioactive decay. While for the second order reaction, this can happen if one reactant is consumed at a rate proportional to the square of the reactant concentration. That is, rate is equal to K into concentration of A raised to power 2. Or both reactants are consumed nearly over time. That is, rate is equal to K into concentration of A and concentration of B. The unit of rate constant for a secondary reaction is per meter per second. In general, a second order reaction takes the form 2A, that is 2 multiplied by reactant will give us the product. While in the mixed order reaction, the mixed order reaction have a fractional order, e.g., rate can be equal to K into concentration of A raised to power 1 all over 3. Then what do we mean by solubility and solubility of ionic solids? Solubility is a result of an interaction between polar water molecules and the ions which make up a crystal. When two aqueous solutions are mixed, the ions interact to form products. That is, AB aqueous plus CD aqueous to give us the products. The reaction is generally a double replacement reaction in the form of AB aqueous plus CD aqueous to give us AD plus CD aqueous. And the solubility rules. It says that rules are a useful guideline to predict whether a compound will dissolve or form a precipitate. There are many other factors that affect solubility, but these rules are a good first step to determine the outcome of aqueous reaction. This marks the end of this session. Thank you for listening.